Hello, this is a presentation of our work on multi-view brain HyperConnectome AutoEncoder for brain state classification by myself, Ines Bouzi, and my colleague Aline Banka under the mentorship of Dr. Islam Rekik. What is our main goal? Given a set of multi-view brain connectomes of subject S, we aim to learn discriminative and representative latent codes of each subject by capitalizing on hypergraph structure to ultimately accurately discriminate among brain states. Graph convolution-based methods have been used in the recent years to address the curse of dimensionality and generate a low-dimensional representation of a brain connectome. However, they primarily focus on preserving one-to-one topological relationship between nodes, and they have mostly ignored many-to-many relationships. Furthermore, existing graph embedding techniques cannot be easily adapted to multi-view graph data with heterogeneous distributions. To address the previous limitations, we propose HCAE, a HyperConnectome AutoEncoder which generates discriminative latent codes of brain hyperconnectomes, which in contrast to graph-based solutions preserve the many-to-many relationship between nodes and can be easily extended to multi-view heterogeneous data. The entire architecture of our model is composed of the HyperConnectome construction, encoder, decoder, and the discriminator, which forces adversarial regularization, as well as classification by support vector machines. We will explore each component separately in detail. In order to generate a subject-specific hyperconnectome from multi-view brain graphs, first we represent each brain by a set of brain networks, each representing a connectomic view of the brain. Then we construct a hypergraph for each separate brain view based on k-nearest neighbor algorithm. And lastly, we combine the separate hypergraphs to generate a hyperconnectome which captures all set-to-set connections. Next, we move on with the encoder. It consists of two hypergraph convolutional layers. The layers are trained in a subject-specific manner to extract accurate low-dimensional representations of the hyperconnectomes. We conduct the hypergraph convolution operation according to the formula displayed. Theta represents the values that will be learned through the training process, while L-1 is the output coming from the previous layer. H and W terms serve for node feature aggregation, while the rest of the terms, dV and dE, vector degree and edge degree matrices, are used solely for regularization. The output also goes through an activation function. Afterwards, we use a decoder to reconstruct the hyperconnectomes from the embeddings. The decoder consists of a dense layer. It tries to reconstruct the hyperconnectome from the low-dimensional embedding. To calculate the loss, we compare the reconstructed hyperconnectome to the original one through a similarity function. We use the formula below where we calculate the similarity between the reconstructed hyperconnectome and the original one. Afterwards, we use the calculated loss to complete gradient descent through optimizers such as Atom. Inspired by generative adversarial networks, we utilize a discriminator model in our architecture to force the distribution of the embedding to match the distribution of the original multi-view hyperconnectome. Specifically, we input the original hyperconnectome distribution and the latent embedding to the discriminator, which aligns their distributions. We evaluate the discriminativeness of the embeddings by training the support vector machine. We feed the learned hyperconnectome embeddings of all population to an SVM, which in turn discriminates between two different brain states, specifically in our experimentations AD versus MCI. We evaluated our model with ADNI-GO dataset with the goal to discriminate between mild cognitive impairment and Alzheimer's disease. We used a total of 77 subjects, of which 41 were AD and 36 MCI. All brain connectomes were extracted from structural T1-weighted MRIs. From each MRI, 4 separate views were extracted from different cortical attributes such as maximum principal curvature, cortical thickness, sulcal depth, and average curvature. In our experimentations, we trained the model in a subject-specific manner through TensorFlow and PyTorch. The k-parameter for the nearest neighbor algorithm is optimized for each view. The model is trained for 100 epochs per subject. A support vector machine classifier is also trained for the discriminativeness evaluation. The dataset is divided into 80% training and 20% testing. The SVM is run 100 times with random shuffle, and the mean of the 100 runs is reported as the accuracy rate. We benchmark our HyperConnectome-based methods against adversarial connectome embedding, which is a graph convolution-based geometric autoencoder that only preserves one-to-one relations between nodes. The multi-view framework, HCAE, achieved the highest accuracy rates of all experiments, with 73.69%. In addition, it outperformed ACE in 4 out of 5 experiments, with the ADNI dataset. All in all, our work has 2 main contributions. It considers many-to-many relations between nodes and merges the separate views innately. Therefore, we reach the conclusion that hyperconnectomes are capable of extracting more accurate low-dimensional representations due to their many-to-many relation-preserving nature. However, further improvement in scalability can still be done by making the model sequential rather than subject-specific. Thank you for your attention, and for more, please visit us at basiralab.com.